Hi, and welcome to the New York City Category Theory Seminar. This is our first talk of the spring 2023. Um, yeah, does it say that I'm recording? Because I can't see it because it's full screen.
This meeting is being recorded by the
Perfect.
host. So
Perfect.
yeah.
Okay,
Mhm.
so today we have Igor Baković, and he is talking from Croatia, and he's going to talk about enhanced two adjunctions. Igor, we have a little thing. Before you start, you have to say four pieces of information. You ready? Where you were born, where you did your undergraduate degree, where you did your graduate degree, and where you live now. Okay?
I was born I was born and raised in Split, my hometown, the second biggest city in Croatia. I finished my elementary and high school here. I graduated in Zagreb at the Faculty for Mathematics, and I get my PhD in Ludwig Maximilian's University in Munich. Did I answer everything?
And you're back in Split. And who is your thesis advisor?
Branislav Jurča.
Okay. Okay. Anyways, take it away. So I'll try to keep up with you. Um,
Great,
okay.
great. Thank you. So, okay. So
First part.
the content of this talk is um, the theory which I'm developing for the last 2 years since I returned to mathematics. And it's more like a philosophy because very much influenced by Jean Benabou. While I was in Paris in 2012, we had many discussions, and I had the privilege to learn about vibrations and his generalized vibrations personally from him. Um, Philosophy comes from his criticism towards mathematicians and mathematics, which is developed mostly on the level of objects. And very few properties are derived on the level of morphisms or one cells in some two category of classes of structures. So whenever we have a hierarchy of morphisms which preserve structure more or less tightly, we are in enhanced context. So the context of enhanced two categories is I would say, appropriate one to address this criticism and to investigate universal properties at different levels of one cells in two categories. So, Noson, you can
Just
move the slide around.
yeah, are you gonna the word enhanced is different than an enriched. So
Exactly.
you're gonna make a
Exactly. So,
distinction.
so,
Okay.
so, so the word enhanced means enriched in F. So enhanced is a special type of enrichment, actually, with respect to the category, whose objects are functors, which are by definition injective on objects and fully faithful. So when Lack and Shulman introduced this category, monoidal category or monoidal two category, everything is correct. What I said, it's Cartesian closed, and they introduced it in 2012 in order to investigate behavior of two monads. So they had their own, let's say, reasons why they did it, and they developed a fair amount of theory in their paper, but very big portion of the theory didn't existed in that paper reasonably, of course, which was already a big paper. So I one of starting impetus for my research, besides huge influence by Jean Benabou, was reading of paper by Walker, in which he proved that whenever one has a Lack side, a potent two monad, uh, two category with such two monad on it satisfies all the axioms of Yoneda structures besides the existence of a right ideal of maps. So
Igor, can we just back up for a second? We start with
Mhm.
the category F, whose objects are injective on objects.
Exactly.
So no, that usually a map is injective, not a category.
Yeah. So injective on objects. So it means that that the part of the functor, which is a function on objects, is injective. So
So
if
you're
you
saying the objects are functors then?
sorry.
You're saying the objects are kinds of functors?
So objects are functors. Exactly. So
Okay.
like the image shows, our objects are denoted by J. So J with the subscript A on the left and with the subscript B on the right. So you have two objects, and these vertical things are just functors with these properties, injective on objects and fully faithful. If you want to think about them differently, it's just a category with a distinguished class of objects. That's it. You picked some objects among all objects. You picked some which you called tight, and this is your category with a distinguished class of tight objects. So one cells are just commuting squares, and two cells are cylinders next to it on the right side between two one cells. And Lack and Shulman, of course, realized. I mean, it's a triviality that this category is Cartesian closed. Actually, these factors.
Yeah.
Mhm.
One second, back up. So let's go through it. So this is a two category, and the zero cells are categories: A of t and B of t, and A of lambda and B of lambda. Those are categories.
Exactly. So
Okay.
so which we call tight and loose part. As I said, uh, uh,
So
objects are functors.
t for tight and lambda for loose.
Exactly.
Okay, and the only thing you assume is the J subscripts are the subscripts are messed up on the right hand side, are injective.
Exactly. There are monomorphisms in cat, special type of monomorphisms in cat, because the most general monomorphism in cat are functors which are injective on objects and faithful. So you don't need fullness in order to be a monomorphism. So basically, functor is composed of two parts. Part which acts on objects and the part which acts on morphisms, either locally or globally, if you like. So if the part which is responsible for mapping objects is injective function, and if it is locally fully faithful, meaning bijective on locally on morphisms, you have an object of our category. So this category is Cartesian closed, and it is a right class of a factorization system, because we can move on also with
Okay, just before we move on. So basically, the left-hand square says that tight objects go to functors take tight objects to tight objects.
exactly.
And the right square says that natural transformations take tight. There are natural transformations that take tight object that go from tight objects to tight objects. Or is that something like that?
Omega tau is just a restriction of omega lambda, because vertical functors ji and jb are just embeddings of a smaller category into the bigger one, which is fully faithful. So omega tau is just sum of omega lambdas, and those which are indexed by objects which are tight. So basically, nothing fancy. Omega tau is just a restriction of omega lambda.
Okay, good. Okay, so now we're gonna go.
Mhm.
Okay, fine.
So Lack and Shulman in their paper investigated certain properties of that category. I mentioned that it's a right class of a strict factorization system on two category of categories. The corresponding left class is a class of surjective functors which are surjective on objects. We will see later that there's a ternary factorization system, but let's move on. So I will try to follow in this way what I wrote. So since F is reflective in cat square, so in the category, actually two category in which objects are all functors, I will make a comment here. This is
By cat square, you mean the arrow category, not
exactly,
okay, fine.
exactly.
So okay, fine.
Objects are functors, any functors, not any more functors which are just fully faithful and injective on objects. So this was an approach by Jean Benabou, who would call them just generalized fibrations. So he has a long time ago theorem which compares and identifies functors over the fixed base and commuting triangles as one cells and obvious notion of a two cell with a Grothendieck construction which he generalized to the case that on the other side you have lax functors from B-op, where B is your base, to distributors. So this kind of Grothendieck construction gives you correspondence. By the way, it's one of primal examples of enhanced equivalence, not just equivalence, but of enhanced equivalence in the sense of this talk. I hope we will get there. But there's two equivalence between two categories. On one side, there's a category whose objects are functors. One cells are commuting squares and two cells are cylinders. And on the other side, there's a suitable two category in which objects are lax functors from the opposite of the base to distributors. So the restriction of this construction tells you just that you have an equivalence between pseudo functors to cat and fibrations, or lax functors to cat and pre-fibrations, or lax functors from B-op to distributors and Condorcet fibrations, and so on and so on. So basically, this philosophy tells you that either you can change the nature of your functor, whether it is lax, pseudo, or you can change the codomain. So you can choose anything in between cat and dist. So you restrict your attention to some sub-category of distributors, and you obtain a more special generalized kind of a fibration. So this is just a comment of how he looked at things from the vibrational point of view. So we can move on with so this is just how we calculate how Lack and Shulman calculated limits and co-limits of just by taking reflection of the co-limit which is calculated in cat square, like in functor category, as you said. We can move on. The category of enhanced categories or full embeddings, as it was called by Lack and Shulman, can be enriched to an enhanced two category because we have this diagram on the bottom, which we call loose functor. It means that although we have and we remember both on left and right side which objects in A and which objects in B are tight, we do not have a correspondence between them. We just have a correspondence via functor f lambda between their bases. So we basically, this says that you have a functor which does not preserve tightness of the objects. This is the meaning of this diagram. So we can move on.
Can we back up a second?
Of course.
You said the purpose of this is to the main purpose was two monads. In other words, the category of algebras for two monads
exactly.
are enhanced.
Which is a primal example of an enhanced two category, because whichever flavor of algebra you choose, whether it is strict, pseudo, or lax algebra, once when you fixed it, you have different notions of morphisms between them. They may be lax or co-lax or pseudo or strict, and therefore you have a hierarchy of morphisms, one cells, in the two category of T algebras, and therefore enhanced two category. Or if there are more layers of one cells, we don't call them anymore F category, F for enhanced, but F2 or F3 and so on. So I didn't put this remark, which I will say right now, in my talk, because I didn't want to confuse the audience. Your advice was very fair, to be as clear as I can. But let me just say that there exists a tree fibration. So fibration between two different tri-categories or gray categories, in which the base is a tri-category whose objects are bi-categories, and fibers. I will not go into details what are one cells and two cells. Part of it we will see in this talk, but the fibers are just embeddings of bi-categories into the base, meaning sub bi-categories of tight maps. So these layers of tight maps are just in the fiber of this tri-fibration. So Fn means just a n simplex in the fiber of these three fibration, which is the discrete as it gets, as a three-dimensional analogon of just subset fibration, because that would be zero-dimensional primordial example of the fibration in logic, for example.
Okay, stop. First of all, an enhanced two category. So I know what an enhanced category is. An enhanced two category will have also tight objects and loose objects, and
so very good question. So the theory is really big, but because we can have situations in which we don't differentiate only between one cells. We can have more type of zero cells objects or more type of two cells. So if you think about F and what are the objects of F, well, they are enhanced categories or full embeddings, as they christened by Lack and Shulman. But basically, these are just categories which are special in the sense that they have a certain subclass of objects which we call tight. So if you enrich in this two category or monoidal category, if you like, then you will just tightness of objects will be responsible in the enrichment for the tightness of one cells in your enhanced two category. So basically you end up with a definition that the enrichment in F, since it picks for any two objects an enhanced category, meaning a category with a distinguished class of tight objects, these now in the enrichment becomes one cells. So basically you end up with a definition that the enhanced two category is just the two functor, which is bijective on objects, faithful on one cells, and locally fully faithful. So basically 0 and 2 cells are the same, but you have some more special one cells than the others, which we called tight.
Stop. Let's go through a nice example. You have the two monad of monoidal categories. Okay. So then that gives you the two category of the algebras of this two monad is the two category of all monoidal categories.
Yes.
Okay, good. Now, what are the tight?
You have lax monoidal functors and pseudo monoidal functors, and these are the two different levels we call pseudo, or if you like strict, but pseudo you call tight, and lax monoidal functors are loose.
Thank you. That's perfect. That's an important. That's
You're welcome.
okay. Now we can go on. Sorry, I'm pestering you.
No.
It's better. Okay, good. Go on. What additional structures there? Okay.
So here I emphasize a connection between the theory of enhanced two categories and its philosophy of paying more attention to morphisms than to the objects with factorization systems, because ternary factorization systems, which are by definition defined by the embedding of one factorization system into another, meaning that the left class of the first one is a subclass of the left class of the second one, or equivalently, right class of the second one is a subclass of the right class of the first one. That's by definition ternary factorization system. So one distinguished ternary factorization system and the strict one on CAT is just this one with which I started. The left factorization system is left class are functors, which are surjective on objects and full, and the right class are just faithful embeddings. So these are just monomorphisms in CAT. They are precisely monomorphisms in CAT. So functors which are injective on both levels, on the levels of objects and on the level of morphisms. And the other one is just the factorization system in which are objects of our study, and these are full embeddings or enhanced categories, is a right class. Left class are just a class of functors which are surjective on objects, and that's it. Both are factorization systems. One embeds into the other, and we call it a ternary factorization system. If you check, for example, in NLab, there's a nice page on stuff, structure, and property, and this ternary factorization system is very much important in describing in which situation certain forgetful functors forget at most structure or at most property or at most stuff and so on. So these are very important in my mind parts of mathematics which one needs to understand if he wants to go deep as he can. So we can move to the next one. Every ternary factor. The last remark is that every ternary factorization system, which by definition is an embedding of one into the other, generates these three classes of maps. And in our situation, these are the maps on the next page. Classes of maps surjective on objects and full stands for the first one. Both stands for bijective on objects and faithful, and the last class is the class of our objects of study, fully faithful inclusions or full embeddings or enhanced categories. You can choose your preferred name. So this is the remark that this kind of situation with the ternary factorization system comes from homotopy theory. You have so-called Postnikov tower and the so-called image factorization, which is not very much related to what I would like to say in this talk, because when I started to produce these slides, I realized that we will barely finish to the enhanced adjunctions. So I think we can move on.
Okay.
Yeah, but if you have any questions, please feel free to.
So these are just many examples of these factorization systems.
Actually, one embeds into the other. So, which this tree simplex says just that, because all arrows on the edges of these tree simplex are embeddings of factorization systems, meaning left class embeds to the left class of the next one, or right class of the next one is a subclass of the right class of the previous one. By definition, you know. Okay. So
Sorry, question.
Can you just say one comment? Yeah. Can you just go back one slide?
More.
I know you didn't want to talk about it. Could you just say something about how this is related to the Postnikov towers factorization?
You have this n-connected, n-truncated factorization system. So if you think, for example, in groupoids, you have one image, two image, three image of an n functor. If I recall correctly, if you have, for example, functor from A to B, then one image is a category in which objects are the objects of the domain, and morphisms are, by definition, morphisms between images of these objects in the codomain. And you can repeat this process n times in order to obtain a Postnikov tower of images of the functor, which gives you a factorization system as this one. Does this answer your question?
I'm just a little confused. Why do we have three classes of morphisms?
So three classes of morphisms are generated in a certain precise way by the embedding of one factorization system into the other, because either you can when you start with any morphism whatsoever, since you have two factorization systems, you can choose the first factorization system or the second one to start with and to factorize your one cell. But when you factorized it by one factorization system, then you can one of these components factorize by means of the other factorization system, and then you obtain the three components out of two factorization systems. And perhaps this answer your question.
I see now. Thank you. Yeah, that
You're welcome. You're welcome. Okay. So yeah. So we have these loose one cells. Basically, as I already commented to Noson, these are just functors between loose parts. So these functors does not preserve the property of the tightness of the object, because tight objects are upstairs in A tau and B tau. So we have functors. If we had a functor F tau between tight parts, this square would say that it's a functor which preserves tightness of the objects. But here we don't have such situation. On the contrary, below it, we have not just anymore a commuting square, but you have diagonal inside of it. This means that this F without a subscript sends all objects from the domain to tight objects in the codomain. So the image of any object, not just of tight object, is a tight object in B. So this is the meaning. So these are the types of one cells, which I discovered by thinking about different situations. And if you move to the next slide, we will see that they are one cells in a particular two category, which comes on the top of Lack and Shulman's category, in which tight and loose cells are just enhanced and loose functors. So with my discovery of the third type of one cell in F, and moreover, the class of this tight functors is a right ideal with respect to loose functors, which is very important because these kind of situations.
Can I ask a question? What is a right ideal?
So right ideal of maps is by definition a class of maps which is closed by precomposition with any other one cell in the two category.
Thank you.
So you're welcome. So you have these two functor internal home for a closed structure on F, which sends any pair of enhanced categories to enhanced category whose objects are loose functors, period. But tight objects are tight functors, meaning those squares which are filled with the diagonal, or in other words, those functors which send any object from the domain to a tight object in the codomain. The unit, so it's you can, if you like, you can check the diagram. But
you want me to back up?
Yes, please. Yeah, exactly. So as any closed structure, it is defined by not just by its internal home, but also by its unit. And the unit for this closed structure is different from the unit for the Cartesian closed structure, because the unit for the Cartesian closed structure is just identity on a terminal category. Here, it is a canonical and unique functor from the empty category to a terminal category. Regardless, this functor is canonical. I believe I had a discussion with Fosco Loregian a few days ago, and it was all about this functor. They have a paper on unicity of formal category theories, in which they compare Yoneda structures with pro-aero equipments in the sense of wood, and they have the chapter in which is called, I believe, the importance of being one. So that's this one. I hope I will come to explain to you when we come to enhanced adjunctions that if you have your Yoneda structure on the two category, then your P, just consider what P does to this functor. So if P is your pre-shift category, pre-shifts on the empty category is just your, there's only one pre-shift, empty pre-shift, so it's just one. But pre-shifts on a terminal category is the whole category of sets. So you have on the one side a terminal category, and on the other side the category of sets. So if the embedding of a terminal category into the category of sets has a certain property, and these properties are responsible to defining Grothendieck construction by certain pullbacks and comma objects with respect to this embedding, then you can conclude a lot about Yoneda structure just by the behavior of your pre-shift construction to this particular functor, which I denoted by 1 lambda. I hope I will have more time to raise this particular important issue. But anyway, just once again on the back. So yeah, here I just describe what does this closed structure to enhanced functors. So we can move on. But basically, it is important to remember that square brackets denote a enhanced category in which loose objects are loose functors those that do not preserve tightness of objects, but tight objects are functors on the opposite extreme, which sends every object tight or loose to a tight object in the codomain. So you don't have any more morphisms of F, which are just enhanced functors or commuting squares. And this is just a proof that this is a closed, not the proof that it's a closed structure, but just here in front of you, you can see that the definition is well defined. And if you go to the next slide, this is just the way how you represent the action of your closed structure on natural transformations, so that the bottom and top square are just components indexed by objects, namely object A, of the composite natural transformation. And this is how the proof looks like. So we can move on. This is a crucial remark. And the theorem, actually, I don't know why my compiler erased theorem with this black line, but anyway, these two functor, I will repeat, square brackets means enhanced category. So for any two enhanced categories, square brackets and these two categories inside them mean loose functors and tight functors from the domain to the codomain. So it's an enhanced category because tight are distinguished among loose functors, and the categories which are enriched in the sense of Eilenberg and Kelly in their milestone paper from La Jolla conference in 1966 defines also enrichment with respect to closed structure, because this closed structure doesn't have to be a monoidal structure. So you can always, if I stop for the moment, if you want to compare a closed structure on a category with a monoidal structure, you can derive a tensor product. But this tensor from the closed structure by adjunction mechanisms. But this tensor product doesn't have to be a monoidal product, in the sense that either the associativity constraint may be only natural transformation and not natural isomorphism, or the same thing for the identity. In this situation, I don't have that in these slides because I had to encircle one finite amount of data which I would like to present. But this closed structure has a corresponding tensor product which is skew monoidal, in the sense that associativity is natural isomorphism, but you don't have an identity anymore, in the sense that it is both left and right identity. It is only right identity. So skew monoidal categories were introduced by Slachany in the world of Hopf algebroids, but they are now ubiquitous around mathematics, so you can find them everywhere. They are less known than their counterparts, monoidal categories, but they are very important. As a part of the data of an enrichment of a category in the closed structure, not in a monoidal structure, although to agree once when you realize that there is derived skew monoidal structure of this closed structure, the enrichments are the same between them, but as a part of the data, you can see these two enhanced functors. So domain of the first one is your embedding of the empty category to the terminal one, and if it is enhanced functor, you can just see what it does on the domain and codomain of one lambda. So domain is an empty functor, so you can have only empty functor to the tight part of the endomorphism home category of A, and basically JA sends this to the identity of A, and this identity will be admissible, for example, in Yoneda structure, if and only if this JA lifts to 1 tau. It means identity on a terminal category. It may look to you that these details are less important, but they are fundamental, at least from the perspective of size issues and categories of smallness, locally smallness, and so on. But I will not go into this. It's a huge story, so I need to stop somewhere. I was able to define, so it was horrible. So I was drawing this diagram for 1 month or something like that, and I finished it in Glasgow. I stood with my friend Bruno Gavranovic at one conference, and I finished it in his apartment. But it's a Stashev associahedron with, I don't know, 50 something vertices inside, and basically this definition, as much as it is complicated on the paper, says very basic stuff orally. And this is whenever you have a composable pair of one cells, you Lax functor compares the images of this composable pair with the coherence 2 cell in one direction, okay? And pseudo functor says that this coherence 2 cell is an isomorphism. Enhanced Lax functor in this context will be an isomorphism by definition if in your composable pair the first one, only the first one, or only the second one is tight, depending whether you are working with the right ideal of maps or a left ideal of maps. So basically it's a Lax functor in which constraints for the composition are isomorphisms whenever one of these is tight or admissible, if you like. So I was also able to why is this important? It is important because, for example, in Gray's monograph on formal category theory, you have a notion of when is the action of Lax functor on a Lax natural transformation defined. Because if you have a Lax, so it is well known that until now, we didn't have neither a bicategory or a tricategory in which Lax functors and Lax natural transformations are assembled into one bicategory or tricategory. They cannot be one cells or two cells in the same tricategory. And in enhanced context helps you to establish that they are, after all, in the same two category, but because of the nature of the Lax functor, they are designed so that they have a well-defined action on Lax natural transformation, which was not the case previously. And this technical condition, which I described you by composable pair of one cells, says precisely that Lax functors have a well-defined action on the Lax natural transformations, and they are indeed 1 and 2 cells in a 2 category, which you will see later. So here, yeah, so for any 2 enriched categories in this closed structure, meaning 2 categories with the right ideal of maps, you have a corresponding internal home. So you have enriched Lax functors, enriched transformations, and enriched modifications, and therefore you have a functor as it is displayed by the last line. And the theory of Yoneda structures by Street and Walters has a really natural and beautiful description in this context, because all these horrible diagrams from Street and Walters paper becomes very conceptually clean once when you realize that what you start with is already enriched category. So because the axioms for the Yoneda structure says you have a two category, you have a right ideal of maps, which we call admissible, and from other axioms you derive the existence of pseudo functor P, which acts on the subcategory of admissible objects to the large ones. But this is just a part of enhanced modules, which are enhanced analogon of Benabou's distributors. You don't have any more functors from B op times A to Z, but you have two functors from B op times A to F. This is by definition enhanced module. They have their own composition, again by Cohen formula, and it is the basis of the approach to Yoneda structures, which I'm developing right now. So we can move on. There's a second closed structure on the category of enhanced categories, and it is defined by a functor which takes any pair of enhanced categories, not anymore to the category in which loose objects are loose functors, but they are enhanced functors. So really commuting squares, but tight objects are the same as in the previous structure. So tight objects are tight functors and loose objects are enhanced functors. So meaning commuting squares. This is enhanced category. And I here describe how it is defined on one cells. And because the definition is such, it is not defined on Lack and Shulman's two category, F, but it is defined on the enhanced two category, which is moved up one level. So now enhanced functors or commuting squares becomes loose, and tight are tight functors, meaning sending every object whatsoever, tight or loose, it sends it to the tight. It is a closed structure, another one, but which enrichment with respect to it gives you a two-sided ideal, not just a right ideal. If you want to get a left ideal of maps, you enrich in F op with respect to previous closed structure. So we can move on. Enhanced bicategory consists now of a homomorphism of bicategories which with these properties: bijective on objects, faithful, and locally fully faithful. So what this means is that B tau and B lambda are different just on the level of one cells. So they have same 0 cells and 2 cells. The difference is just that tight one cells are in the domain and all one cells are in the codomain. And we call this low domain tight part, and codomain we call loose part. Okay, we can move on.
Can you 1 second. Can you give an example of such a thing from two monads?
It is just embedding of once when you fix the notion of algebra, strict pseudo or whatever, you have an embedding of pseudo morphisms of algebras into lax or co-lax morphisms of algebras. So every pseudo morphism of algebra is lax, but not vice versa.
Okay, so the bijective of an object means
The objects are the same.
the objects are the
Algebras,
same, and
yes.
the only thing is, in one, the morphisms are a little looser than the other.
Exactly.
Okay.
Exactly. And that's the whole philosophy of enhanced categories. Precisely your last sentence. Certain one cells are looser than the others, and that's it. That's the philosophy. So when you have two enhanced bicategories, how we define a lax or co-lax functor, whatever name you choose, I'm fine with it as long as you understand that there are four types of them. So if you look at this square, and especially at the last formula on the slide, which is just a name for the coherence of composition, this coherence could go other way around, and then we would have a comorphism, not a morphism. Morphism meaning lax functor, and comorphism meaning co-lax functor. So whatever name you choose, you just understand that these phi can go in one direction or another direction. And if we stick with this direction, then there are two types of a morphism. And when this phi will be an isomorphism, we'll decide which type of it is. So I call them, because of dualities in two-dimensional algebra, I call them morphisms, comorphisms, coopmorphisms, and what the opmorphisms, of course, just on the basis when this phi is an isomorphism. With such definition, you have four different two categories, strict two categories. So one important point. I chose a name, strongly enhanced bicategories, for those homomorphisms of bicategories whose domain is a strict two category. But these kind of gadgets abound in mathematics. For example, every pro-aero equipment in the sense of wood is such. I'm not aware of any equipment. Maybe anyone from you can give me a counter example, but any canonical equipment has a strict two categories as a domain, or even one category as a domain. So for example, embedding of cat into distributors, or embedding of set into relations, it's just one category as a domain. So I'm not aware of any particular example in which bicategory is a domain, only it is a codomain. Why is this important? It is important because all these four categories, four enhanced two categories, whose existence I proved, rely on the fact that the composition is defined by means of the domain, which is a strict two category. Therefore, the composition is strict, and you end up with a strict two category. Although you have objects which looks like bicategories, you know. So it's a very let's say important thing that we can assemble certain types of bicategories, like equipment, into a strict two category, in which also the one cells are not strict, but they are lax and co-lax in a certain enhanced meaning. So yeah, okay. I commented on
So Igor, you got to keep an eye on the time, all right?
How long do I have?
How about 10 more minutes, because there might be questions afterwards. So
Yeah. Okay.
it's a lot of material. It's
Yeah, exactly. And I was afraid, and actually on the slides we will not even get to enhanced
adjunctions.
adjunctions, but the last sentence, which I said, just gives you a way how we produce them, because I established the existence of a certain two category. And adjunctions, enhanced adjunctions, are just internal adjunctions in these two categories. So basically, but I'll give you examples, because when I started to write down these slides, there were so many examples, as I announced in my talk, and I should be fair and to mention maybe the most important. And this is, for example, whenever you have an enhanced adjunction, you might be in the situation that the left adjoint is always lax, and left adjoint is always colax, and the right adjoint is always lax. This may be an adjunction, even though you don't need to, or may be possible to compose the two. I didn't write another fact also, which I proved, and that is the existence of a strict double category, strict, in which objects are again enhanced by categories, in which horizontal one cells are lax functors, vertical are colax functors, but the squares are so-called generalized transformations or rope transformations. These are kind of transformations between lax and colax functors. Even though you cannot compose lax and the colax functor, there's a still meaningful notion of the transformation between them. It looks like a distributive law. And these are the squares in the strict double category. It was very troublesome to prove the existence, or for example, the interchange law, that this is indeed interchange law between squares, that which makes this in the strict double category. But if you recall that, even if you start, for example, from pseudo double categories, pseudo double categories assemble also into the strict double category. So this is the corresponding, let's say, fact on the side on the double categories. But if we go back to enhanced categories, there's Mike Shulman gave a recipe how to compare the two. So, for example, if you start with enhanced category, which comes from the equipment, in the sense that, again, you have a domain two category and codomain bicategory, you can always cook up a double category from the recipe which he gave in the appendix of his monoidal fibrations and framed bicategories. But the point is that we do have a strict two category of enhanced bicategories, and the enhanced adjunctions are adjunctions in this strict two category. What are the one cells and two cells? Well, once you have four strict two categories, and one cells are lax functors or colax functors, and two cells are transformations whose components indexed by objects are tight. This is very important, because tightness of these components indexed by objects are responsible for strict associativity of on the level of both one cells and two cells. So even if I put some pictures of the universal properties which generates enhanced two adjunctions, it wouldn't be much clearer for you, but it might help you to say that, for example, one of the most important examples is a reflection of fibrations, Grothendieck fibrations in all functors. So what I'm saying is that you have enhanced two adjunctions between, on the left side, a two category whose objects are Grothendieck fibrations, whose tight and loose cells are Cartesian functors between fibrations, meaning preserving Cartesian morphisms, and loose cells are any functors which just commute with fibrations but do not necessarily preserve Cartesian morphisms. This is a two category on one side with the corresponding notion of a two cell. On the other side, you have what we started with, cat square. So Nelson said arrow category or functor category, but basically objects are functors, not just fibrations, but any functors. So fib as a two category is lax reflexive in this two category, and it generates a two adjunction, enhanced two adjunction, and the two monad, which we call associated two monad. I'm very, very much excited by my discovery a few days ago that these two monad is admissible in the sense of Bunge and Funk. We say that the lax idempotent or co-lax idempotent two monad is admissible if a certain bicomma object condition on your two category is fulfilled. But it's a technical, and it means just that first we have a notion of admissible one cell. We say that one cell is admissible if T of when X on it is sent to left adjoint. So admissible cells are sent by your monad to left adjoints. And these admissible one cells are required to possess a certain stability property with respect to comma squares. But to conclude, admissible monads are two-dimensional analogon, correct analogon of Cartesian monads. Cartesian monads are those which whose natural transformations corresponding to unity and multiplication are pullback squares, and they allow you to form a generalized multi-categories, in a sense that you produce a Kleisli category whose objects are spans in which one leg goes to T of your for example, for free monoid monad, you produce out of this span, which is just a monoid in the Kleisli category, you produce a multi-category. Associated fibration is admissible, and whenever you have an admissible two monad, which is born by enhanced two adjunction, for example, you can cook up a tri-category of spans. Not anymore bicategory of spans, but tri-category of spans. And this stability of these comma squares tells you that you can horizontally compose spans and morphisms of spans which are filled with two cells in triangles. You don't have any more span up and down and just a vertical cell between them, but there's something in the triangles. And these comma squares and their universal properties allow you to compose horizontally such morphisms of spans. So you end up with a tri-category and pseudo monoids, and I will conclude with that, in a tri-category, in a Kleisli tri-category, in which one cells go from A to PB are precisely multi T bicategories, which was left as something to be investigated by, for example, Mike Shulman when he axiomatized duality involutions for two categories like op and so on. So I will stop here, and I will gladly.
Okay. Thank you very much. Thank you. We're all clapping. Hold on, you can't see me clapping, but I'm clapping. I just want to go through the rest of the slides. Okay, this is the sources. Any questions? Emilio, go.
Yeah. So I just wanted to kind of get an overall understanding of the talk with just an example. So if you have two monads and you look at the two category of algebras of the two monads, that's giving you an example of these enhanced bicategories, right?
Exactly.
And then, so then what's the two category exactly that's containing those?
So you have a two category which you started with, and you have a two category of your algebras.
Mm-hmm.
There's a forgetful two functor from algebras to your two category which you started with, and if this forgetful two functor admits a left to a joint, you are in the situation that you have enhanced adjunction. Because if you started with an enhanced two category, but not all examples of enhanced two categories comes as algebras over a two monad. Examples, very important examples are, for example, embedding of cat square into cat square filled with two cell in one direction. So tight maps are commuting squares, and the loose maps are squares with the two cell in upwards, for example, direction. Third class of examples are equipments in the sense of wood. You have bijective on objects and faithful and locally fully faithful, and additionally homomorphisms in which every tight map one cell acquires a right adjoint in the codomain. So, for example, inclusion of cat into distributors says that every functor has a right adjoint in the world of distributors. Yeah? So this is the very important class of examples, which is not of the type T-alg for T. But whenever you have, in fact, a two monad, these two monad, even if it is, this is very important. If you start with an ordinary two category, not enhanced two category, so you have only one type of one cells. If you have a Laxide-potent two monad, so it's of Koch-Zeberlin type, these two monad generates a subclass of your one cells. And these are the cells which are sent to left adjoint by its action. So we call this one cell submissible, and they become tight one cells in the newly established enhanced two category with certain nice properties, for example. So this is how you cook up an enhanced two category out of ordinary two category with an action of two monad on it.
Thank you.
You're welcome.
Anybody else? I have a question. I just want to understand this philosophy of Ben Abu a little bit better. So, for example, let's just talk about monoidal categories. He says instead of looking at the subcategory of strict monoidal categories and the big category of monoidal categories, rather look at all monoidal categories and then look at the morphisms between them. Strict versus lax.
But that's Grothendieck philosophy. He was always saying you know the nature of the object by its relationship with all other objects. So basically, to study an object means to study its transformations or morphisms with other objects. And Jean Ben Abu, I know for the fact, was a follower of the Grothendieck like myself. So this is the type of structures which allow you to investigate more closely the properties of functors, the properties of one cells. not just the properties of objects themselves. His favorite example was Grothendieck vibrations. He says, nowadays everybody knows about vibrations, but nobody has a clue about the properties of Cartesian functors. So the functors which preserve the nature of the Grothendieck vibration, because Grothendieck vibration is defined by liftings of cells which are Cartesian. And of course, that nice functor between vibrations should preserve its structure, meaning preserve Cartesian morphisms in the domain. But functors which do not preserve them are also legitimate to investigate. What I'm saying is that Cartesian functors possesses certain universal properties, not just with respect to other Cartesian functors, but with respect to all functors between vibrations. And we always have in the enhanced context the relationship between tight and loose cells, in the sense that tight cells may have universal properties which do not apply only to tight cells, but to both tight and loose cells. So this is the kind of situation which we constantly have in the world of enhanced two categories.
Okay. Yeah, Igor, somebody asked on the chat if you have a paper or slide, or the slides will be available.
So the paper will be very soon. It will be the first one after 12 years, but it will be introductory paper for all the branches of the theory which diverges from it. So I'm developing these Yoneda structures in the enhanced context. So I told you that I proved that there exists a strict double category of such things, and that the Lacks and the local adjunctions, which are very much important in the change of base situations. So whenever you switch from internal category theory or enriched category theory of fibered category theory. So whenever you move between different contexts of nature of categories, you are almost certainly need to deal with local adjunctions between bicategories basically in the change of base situations. So this paper, the first one, hopefully even next week or week after that, will be on archive, and it will be a compendium of definitions and universal properties which give born to enhanced two adjunctions. And basically these are just certain generalizations of liftings and Kahn extensions, you know. So
right.
Yeah.
Do you mind if I post the slides?
No, I don't mind. I don't mind.
So I'll put up the slides with the YouTube.
No problem.
Okay. Anyways, thank you very much. I think, well, like you said, it's a whole world out there.
Yes, exactly. It's a huge world.
We got to peek into it. Okay.
Exactly.
I just want to make one little advertisement. Next week, we're starting a 3-part series on TQFT and computation, and Mikhail Kovanov will be speaking on universal constructions and its applications. So that should be very interesting. You're all welcome to come.
Thank you, Nelson.
Right, Nelson?
Say again?
Those are all going to be in person, correct?
That's going to be in person, but I'm going to try to, I don't know, maybe make it a Zoom and in person, some type of hybrid type of thing, so that more people can ask questions or something like that.
Super, thank you.
And Nelson, if you can make it hybrid, it will be great, because we cannot enter the GC.
Right.
Because,
okay.
You know, those of us who are not vaccinated.
Okay. I will try. But if not, then it will be, you know, I'll put up the video a few hours after the talk on YouTube. Ladies and gentlemen, it's a pleasure, and thank you, Igor. Thank you very much. Very interesting.
Thank you, Nelson.
Thank you. Take care.